Hello everyone, welcome to my channel Coding Together. My name is Vikas Oja. Today we will see a new data structure, that is disjoint set data structure. So it's a data structure that is widely used in solving graph problems. So let's start with it. So as we know that set is a group of elements, and when we say disjoint set, it means when the two sets are not overlapping, or the intersection of those two sets is a null set. So if we have a look here, the S1, S2, S3, S4 are the disjoint sets because no two set is overlapping, or the intersection between any two set is a null set. And disjoint set data structure maintains and stores these collections of disjoint sets, and each disjoint set is represented by a representative. So for disjoint set S1, the representative is highlighted by the red element C, and for set 2 the representative is E. Similarly for S3 and S4, the representative are A and B respectively. So let's see some of the operations that we can perform on these data structures. First is find. So whenever we say find of A, that means we have to find the representative of the set in which A belongs. So A belongs to the set S3, and we have to return the representative of it, that is A. Now when we do find of D, that means we have to find the representative of set in which D belongs, that is C. So D belongs to set S1 and the representative of S1 is C. Now the next operation is union. So whenever we say union A comma B, it means we have to find the representative of the set in which A belongs, and also the representative of the set in which B belongs, and we have to merge those two disjoint sets. So if we see, S3 and S4 are the sets in which A and B belongs, and the representative are A and B respectively. So if we perform union, it will be like this. These two disjoint sets will be converted into one disjoint set S3, and the representative of this new disjoint set will be A. Now how can we implement this data structure? So we will use a tree implementation. So let's assume that we have a disjoint set which has element A, B, C, and A is the representative of it. Now the corresponding tree implementation will contain a root node, that is A, and that will be the representative of the tree. The root node will be the representative, and other two elements B and C will be the nodes of the tree. Now we need to know there has to be some relationship between the root element of the tree and the other nodes. Either they need to be directly or indirectly connected to the root node. So here we have what is called parent pointer representation. So what is parent pointer representation? Each node in the tree has a parent pointer, and the parent pointer points to the parent of a particular node. So if B is a parent of C, then the parent pointer of C will point to B. And if A is the parent of B, then the parent pointer of B will point to A. For the root element, the parent pointer will point to the root itself. So suppose if we want to know in which tree the node C belongs, we have to first know the root of that tree, right? Because the root represents that tree. And in order to know the root for that node, we need the parent pointer representation, because the information is stored in that parent pointer representation about the relationship between the node and the root. So the parent pointer representation can be done with the help of an array. So if in the above diagram or even in the above tree we have A, B, C as the nodes, then the parent of A will be A, parent of B will be A, and parent of C will be B. And if we start with the node C, and if we want to find the tree in which C belongs or the root of that tree, we will traverse this parent array starting with the node C until we hit a node which is the parent of itself. So we'll start from C and we'll check the parent of C, that is B. Then again we'll check the parent of B, that is A. And again we'll check the parent of A, that is A itself. So we'll stop here and we will say that A is the root of that tree, right? So C belongs to a tree in which A is a root, because A or the root will represent that tree. So that is what we called the find operation. So if we say find of C, we will traverse this parent array starting from the node C. For the C, the parent is B, for B the parent is A, and for A the parent is A. We'll stop here because for A the parent is itself the node A, and we will declare that the root of the node C is A, i.e. C belongs to a tree which is represented by A. So find of C will return A. Now let's see another operation of the tree implementation, that is union. So to understand union in the tree implementation, let's take an example. So at the start we have 4 disjoint sets, 1, 2, 3, 4, or we have 4 distinct trees with only one node, that is the root node, and the parent pointer is pointing to itself. So we have our parent array where each node is written and the parent of each node is represented. So for 1 it's 1, for 2 is 2, and so on. So if we say union 1, 2, it means first find the root for the node 1. So we will perform find of 1, that will find the root for the node 1. So find of 1 is 1, because we'll start with the parent array. We'll iterate the parent array starting with the node 1, and we see that for the node 1 the parent is 1 itself, so we'll stop here and we'll return 1. For 2, again we will perform find of 2. So for find of 2, the value is 2, and then we will combine these two trees, or we will combine these two disjoint sets. So when we say union, the root of one of the tree will go under the root of the first tree. So we will move 1 under 2. So at the root of this tree 1 is 1 itself. So we'll move 1 under the root of the tree 2, that is 2. And we will change the parent. So the parent of 2 is still 2, but the parent of 1 will be changed from 1 to 2. So we will mark it as 2. We'll change it as 2. Now we will perform union 1 comma 3. So what we will find is, first we will find of 1. That is, now we will start recursively scanning our parent array starting from the node 1. So for node 1 the parent is 2, then we'll go to the node 2, and for 2 the parent is 2. So we'll stop here, as the for node 2 the parent is 2 itself. So find of 1 will return 2, and similarly for find of 3 will return 3. So again we will move the root of root 2 under the root 3. And the parent of 3 will remain 3, but the parent of 2 will be changed from 2 to 3. Now again we will perform union 1 comma 4. So we'll again find 1. We'll perform find of 1, that will be 1 to 2, 2 to 3, 3 to 3. So find of 1 will be 3 now, because for the node 1 the root element is 3, and for find of 4 it will be 4. So we will move the root 3 under 4, and the parent of 4 will remain 4, but the parent of 3 will be changed to 4. Now this is the new tree or the new disjoint set if we perform these union operations. So as we have studied union and find and union, let's see the code for the same. So as we can see the code for the find, it takes one input I, and if the parent of I is I itself, then we'll return I, else we'll recursively call find with the parent of I. Now for the code of union, so it takes two input parameters. So first we perform find operation on the node I or the element I. This will give the representative of the I. So find I gives the representative of the I, or in the tree representation it's the root node for the node I. Similarly for the node J or the element J, it will give the representative or the root node of J, and we will change the parent of the root node of I or the representative of I equal to the root node of the J node or the representative of J. So let's talk about the time complexity of these two operations. So as you can see here, that a naive implementation of these two approaches is giving us the linear time complexity. Linear time complexity, that is big O of n, because it's creating an unbalanced tree, right? And we are almost traversing each of the elements. So both for find and union. So can we improvise these time complexities for both the operations? Yes. We will see in the next video how we will improvise these time complexities using path compression and union by rank. So if you like this video, please share and subscribe. It will keep me motivated to bring all these concepts for you. Thank you guys. Bye.